some of these things will, thank you. Yeah. So some of these things will sort of discuss in a bit of detail. I have not uploaded these notes because I want to see how much I can cover in this first talk. Depending on that, just after the talk, I'll upload this particular lecture, and also the tutorials I'll myself do at 2:30. So I'll also upload a set of problems which we can discuss live. I mean, on that whiteboard there. So let me start right away. So I should say that this is should be accessible to anybody without any background, very little background, that is not specified knowledge about either group theory or linear algebra. So whatever we are learning in advanced linear algebra, it may not require that also. There will be intersections also with some of the things people have done. So let me start right away. So as I said, linear groups mean groups of matrices. So as we know, it's all pervading in mathematics. And depending on your taste, if you work over matrices over real or complex fields, then you study groups of matrices, then you study Lie group theory. Over general fields, you study what's called algebraic groups, what are called algebraic groups. And over number rings, number fields, you study what's called arithmetic subgroups. Then over finite fields, you'll require for classification and finite simple groups. Representative theory of finite simple groups require studying linear groups over finite fields. Then generally over any ring, but over any commutative ring, let's say, representation theory is the study of groups of matrices over any ring. Okay, this is roughly the description. So depending on our taste, people can go ahead after these talks, deciding what they want to pursue. Then I can point out to some of the material, some of the substance in textbooks and other papers where you can pursue any of this. So as I said, some of these we'll touch upon, and a few among them we will discuss in detail. So in the beginning, let's start with any field. So if you're sort of comfortable with working over real and complex numbers or over finite fields or rational numbers, keep that in mind. In the beginning, we'll be looking at essentially real and complex because that's probably more common for people who learn linear algebra with a point of view of doing operator theory and so on. So what is the first example of linear group? The set of all n by n matrices which are invertible, non-zero determinant. So in a field, invertible is same thing as saying determinant is non-zero. So the word general linear gives this GL here. By the way, I would, as I said, it's kind of, you don't require much background in understanding what we are doing. Nevertheless, my style is to in between stop and give some light comments by somebody or other, maybe some cartoons relevant to it. Let's see. Okay. First of all, there is a bijection between the group JLNF, that is invertible n by n matrix, a set of all ordered F bases of the n-dimensional vector space F power n. What is the bijection? It simply look at the natural basis, canonical basis E1, E2, En, and given a matrix, you associate to it this new basis GE1, GE2, and GEN. So this is very canonical. It's a bijection, as you can see. So in other words, yeah, somebody wanted to say something? No. In other words, yes. Okay. Do feel free to ask in between, but let's see. We have not started anything right now. So this is a bijection. For a natural number n and a prime number p, what is the cardinality of GL and FP? By using this bijection, you can do this. Okay, we just have to count the columns. If you want, many of you know it already, how to do this. Some of you who are doubtful can do it in a few minutes. And this counting, this is the cardinality of this group by simply counting the number of ordered bases that FP power n has. Maybe some of these, if there are any doubts during the tutorial, we can even discuss that. We'll have problems to discuss, but we can also discuss any kind of doubts, which you may not have been clear about. Yeah? Okay.
Sure, sure.
There is some disturbance. Okay. Now it's okay. Yeah. The special linear group is SL, which is defined as those of determinant 1. This is a subgroup of that. then since determinant is of two matrices over a field, or a determinant of product is product of determinants, then this is nothing but the kernel of this determinant homomorphism. So groups like JLNR and SLNR over phi field are effective because can also not just regard them as groups, but also as topological spaces, giving them topology coming from R, Euclidean topology. And you can use analysis and so on, topology. We'll see a few things. So by the way, if you lay out any n by n matrix as an n squared tuple, then this is just an open sub. So MNR, the n set of n by n matrices is nothing but R to the n square. Okay, just regarding as a topological space, if you like, or as an additive group, MNR is Rn square, and this can be viewed as an open subset. Namely, we have nice continuous function, namely the determinant. Determinant is not equal to 0 function. So this is the open subset of Rn square. Similarly, SLNR is a closed subset. This is an open subset of Rn square. As I said, determinant is clearly a nice function, polynomial function with the n square entries. So polynomial not equal to 0 is an open set of points where it is non-zero is an open set. SLNR similarly, this closed subset Rn square. So orthogonal group consists of, so I'm just introducing some of the key players first before discussing them in together or something like that. So consist of all those matrices whose, I hope you can see there is some blocking here. G transpose is G inverse. So we'll see the reason behind calling the word orthogonal. All of you know probably, but this is the word orthogonal. If you tell us, okay, this is just another word for perpendicular. So as I said, the group of orthogonal matrices consists of those whose transpose is inverse. Okay, the fact that it forms a group, why should it be so surprising? Even elementary facts sometimes can follow very easily by looking at this conceptual way of looking at it. For example, look at this claim. This is an elementary claim. Took 4 real numbers satisfying these equations. A square plus b square is 1. And then how do you prove that a square plus c square is 1, b square? Okay, just think about it for a moment. No. Maybe you can sort of take a minute during tutorials to say things of this kind more generally. So for example, more generally, for a positive integer n and ij less than equal to n, consider the real numbers. Gij satisfy these equations. Remember, gi1, gi2, for all I, it is satisfying this. And here it is satisfied for all I not equal to j. Then prove that we have this other way, g1i plus g2i. So you can easily, when you state it like this, it's immediately clear what we are trying to do. So as I said, this is immediately follows because of viewing something as an element of an orthogonal group. Okay. Proceeding further, SON special orthogonal group is just like special linear. So determinant 1 matrices in ON. So determinant of a matrix in ON, since determinant of G transpose is determinant of G, it is just plus or minus 1. Because it's a real matrix. So determinant of SON is of index 2. Okay, so as I said, determinant is plus minus 1. In particular, has index 2. This is what I just now mentioned. Then the unitary group consists of complex matrices. There should be some care here. Of course, we are just defining them as matrices, matrix groups. When you think of them as Lie groups and so on, if you know what Lie groups are, then you'll be thinking of whether it's a real Lie group or a complex Lie group. So although the matrices are complex, they'll be treated as real groups. Anyway, Lie groups. Determinant of bar is determinant of A bar. A bar simply means the matrix whose entries are all complex conjugates for the original entries. Because of this condition, this implies determinant of G has modulus 1. Okay, complex number of modulus 1. So what about U1? 1 by 1 is just simply SO2, the circle group of e power I theta. This is the group, or you can think of as cos theta, sin theta, minus sin theta, cos theta. We just calculate what is SO2 What are the possible matrices in SO2? You'll find it's just rotation, cos theta, sin theta, minus sin theta, cos theta, which is circle group. U1 is the same thing. The special unitary group is once again those of determinant 1 inside as UN. Okay. Here is so in small dimension, there are some identifications sometimes which are very useful also. For example, SU2 can be naturally identified with the sphere in of unit sphere in dimension 3 of dimension 3. Okay. So how is that? You can easily see that SU2 is a 2 by 2 complex matrices satisfying this. Determinant 1 also. Then you say you can identify it with the unit sphere in 4 dimensions. Okay, so we'll come to that a little bit again soon in a few minutes. So talking about this topology of this metric group in a lot of detail will take a lot of time, and some things have to be introduced. Instead, we'll just discuss a few of these aspects. First of all, for example, connectedness. So we can discuss, this is a well-known thing. JLNR is not connected. Those of positive determinant and those of negative determinant are two connected components. So main thing is to show, of course, they are in different connected components is clear. Determinant is continuous function. So to plus minus 1, positive and negative, then positive ones and negative ones cannot be the same connected component. So what happens is positive ones form a single connected component. That's the main part of this. Meaning there are no more connected components. All the positive ones have the same connected component. All the matrices. In contrast, if you look at complex matrices, JL and C, it will be connected. It will even be path connected. It can connect by path. I mentioned this here. So this is a simple exercise. Again, you can discuss it during tutorial if anybody is interested or doesn't know. It's a nice little proof. So there are quite a few. See, real and complex are in many ways similar, but this kind of things happen. This is not connected. This is connected. And these groups are compact groups. So since we are looking at Euclidean topology, we just have to look at them as closed and bounded. Both these properties are almost apparent from the definitions. Definition of these matrices here are T transpose G bar is empty. Just put this as a condition in n square variables. You find it's a bounded set and also closed condition. So these are compact. So in a few minutes, we'll discuss also exponential map on matrices. And again, return some of these questions. Exponential map helps in studying linear groups, okay, groups of matrices over real and complex numbers. We will just introduce a few linear groups over real and complex numbers. So one more, which is again a very nice classical group, is called symplectic group, defined as the group of all 2n by 2n. So this notation, sometimes some people call it SP2n. Oh, he'll call it SPN. So the 2n by 2n matrices satisfying this condition. Incidentally, if you take SP1, that means elements of, instead of saying SL2R, just take GL2R and satisfying this condition. Automatically, it is of determinant 1. Okay. So what I'm saying is, without putting the SL condition, automatically determinant 1 condition comes. SP1 is just SL2. So symplectic group, this name was given by Hermann Weyl, as you know. Hermann Weyl has this very beautiful book called Classical Groups. Hermann Weyl was a mathematical physicist also, mathematician cum physicist. And he would refer to the general linear group as, like the queen bee. He would call this her all-embracing majesty. Okay, so many of these are subgroups of that, and all of them are subgroups of GLN for appropriate n. So symplectic group, symplectic name was given by him. So as I said, SP2 is SL2R. You can just verify that easily. More generally, if you take 2n cross 2n block matrix, these are n cross n blocks ABCD, then the condition, let's go back. What is the condition? This condition, we rewrite, trivial condition. I mean, just work out, write it as ABCD and multiply it out. And you will get this condition to A transpose C and B transpose D are symmetric, and this condition. Okay, this is the condition for a matrix 2n by 2n matrix belong to SPN. It's a simple calculation. once again, I don't want to spend time here because it's very elementary calculation. Anybody can do it. We might do it in the tutorial if necessary. So together these groups, whatever I introduced now, these examples, this class of groups, people call them as classical groups. So there is no formal definition, but these are the ones which come under classical groups. So subgroups of classical groups also are very important in this subject. And some of them have introduced. They are not really classical groups, but they are subgroups of classical groups. So which are special types of groups. For example, these are the examples. Group of upper triangular invertible n by n matrices. Upper triangular n cross n over a field F and denoted B. Okay, this notation B maybe because nowadays we have this theory of algebraic groups where we call them Borel subgroups. So this is an example of a Borel subgroup. So maybe in the old notation they would call it differently. So group of upper triangular invertible matrices over a field F. Then this is the group of unitriangular matrices in B and F. That is, diagonal entries are all 1. This forms a normal subgroup. And the group of diagonal matrices, invertible matrices. This is, of course, abelian. Diagonal matrices commute. Okay. So some more properties of this we'll discuss in tutorials. Okay, set of n by n matrices, integer entries. Suppose you take special entries like integer entries and determinant plus or minus 1 is denoted by JL and Z. Okay, in general, when you take n by n matrices over something like Z, some other ring, let's say, it may not be a field. When do you form a group? When the matrices have determinant which is invertible element in the ring. So since then only invertible elements are plus minus 1 in Z as a ring, as a multiplicative invertible, only plus minus 1. So this is the group of invertible. So JL and Z by definition is determinant plus minus 1 matrices in M and Z. You can easily see if you take a matrix of determinant plus minus 1, you can find its inverse looking at that joint. Okay, so this is also an important group, and especially for for number theories and people like that, we take GL2Z or SL2Z. These are very important. Riemann surface theory also. And its subgroups. Okay, for any field, the group of scalar matrices is the center. That's clear. You can just say that. What are the things commute with every matrix? You can just look at things commuting with so-called elementary matrices, and you'll get conditions that it has to be scalar. Scalar matrix, lambda, lambda, lambda. Similarly, center of SL and F will be just center of this intersection with SL and F. Since scalar matrix is in SL and F only if it's nth root of unity. Lambda is an nth root of unity. Okay, so you can imagine when F is a finite field, it's a bit subtle to find the center and so on. Because on the one hand, F is a finite field of some cardinality P power R, and you have this nth root of unity. You have to look at the GCD and so on. Okay, that's what I said. What is center of SLNF for a finite field? Okay. Why I'm asking this is because when you study representation theory, representing groups as matrices, center you have to divide out by often. So you have to know how big the center is. Okay, next is this so-called permutation matrices. Given any permutation, so this is a matter of convention, how you put it. The convention we are using at this point is, look at the permutation matrix P sigma, which is rows are R sigma 1, R sigma 2, R sigma n, where R1, R2, Rn, the usual rows of the identity matrix, 1, 0, 0. Okay, so you can look at this columns if you like. So whichever definition you make, it's meaningful, provided when you're using some property about permutations, you should know how you are multiplying permutations and how you are multiplying matrices. So any set of permutation matrices forms a subgroup isomorphic to this under matrix multiplication. I want to say it is just isomorphic to Sn. So meaning what? How do you multiply sigma and tau permutations? So it is always convention, right? Sigma times tau could be sigma composite tau. This means applying tau first and sigma later, or sigma first and tau later. So this way of putting is sigma times tau means sigma first, tau later. And we will. Okay, so I just mentioned here some other properties. So this is the group 1 star 0 1. T2F means 1 star 0 1. This is an abelian group. isomorphic additive group on the star place, additive group of F. Whereas for n bigger than 2, the unit triangular matrices with ones on the diagonal, that is unit triangular matrices, form a nilpotent group. The nilpotent is a generalization of abelian, right? You take the commutator of this group with itself, all xy, x inverse, y inverse group generated by that, that's called the commutator subgroup, and look at commutator of the full group each time. You keep on going there. That is a series. It should stop at a particular finite level, and it's called a nilpotent group. So obviously, abelian groups are nilpotent because first level itself they stop. Becomes identity, that is stop means BNF. This is a, you remember, invertible upper triangular matrices. So this group is the semi-direct product, that means made up of these two. As I said, it is just product of any element here is uniquely an element, a unit triangular times a diagonal matrix. But when you multiply out, write a small b as t tan d, then b1 times b2, when I write t1 d1 times t2 d2, it is not t1 t2 d1 d2 because there is an action, namely diagonals will conjugate the unit triangular to another unit triangle. So this is called semi-direct product. You can easily work it out. This is going to be discussed in tutorial, because we are going to start with simple problems like this in tutorial. This is semi-direct product of these two groups. So this is what is called, this is a solvable group. Okay. So these are all generalizations of abelian group. Abelian, nilpotent, solvable. Abelian is very special. Nilpotent is less special. Solvable is even less special. So these are all kind of generalizations of abelian, if you like. So I'm talking the point of view of people who don't do really group theory and so on. Okay. So other people would know what I mean immediately. I don't have to say that. It's like carrying equal to. Okay. Anyway, determinant of this permutation matrix sigma is the sign of the permutation. You can verify this. How do you verify? You can do any number of ways. Maybe we'll discuss a few ways. You can think of it yourself. Then the set of permutation matrices is a subgroup of not just GLN but ON. Then my second lecture tomorrow, I'll discuss about group of integer matrices. At the time, interesting things will arise. Okay. Anyway, we'll just related to this. Okay. Suppose you want to prove that n factorial divides p power n minus 1, p power n, this product like this for any prime p. You know what happening. So anybody can, maybe you can prove it using some elementary high school mathematics, something like that. But the point of this is that conceptually, how do things follow because of this? Because permutation matrices is isomorphic to the group of Sn. So it is order n factorial, and it is a subgroup of this group SL, GLN FP. GLN FP over a finite field P, that is n by n invertible matrix over Fp, has this cardinality. So this is just Lagrange's theorem applied to that. So such things drop out. You don't have to prove them, it just drops out. So I just mentioned one sort of non-example here. Let us note that this set, so this is not the usual set of invertible matrices. This does form a group, but it is not a subgroup. That's why there is a difference between saying subgroup of GLN and so on. Under the, so it should be invertible matrix in this thing. Okay, so this is okay. So once again, a little bit of pausing here. So I want to make a, we call a comment of Herman Weil. He says that stringent precision attainable for mathematical thought has led many authors to a mode of writing which must give the reader an impression of being shut up in a brightly illuminated cell, where every detail sticks out with the same dazzling clarity, but without relief. I prefer the open landscape under a clear sky with its deep depth of perspective, where the wealth of sharply defined nearby details gradually fades away towards the horizon. So this is a nice way of Herman Weil is very poetic in his expression, and in fact, you can see that he's sort of a physicist also. Sometimes mathematical mentality is just be very rigid and not talk about these things. Okay, let's come back to our mathematics. So orthogonal unitary groups, best way to view them is in terms of usual inner product. So look at the dot product on Rn, which is your this thing, and we know that V dot V gives the square of the length of the vector V. So of course, the cosine of the angle is the dot product for unit vectors. So note that dot product is linear function of both these variables and symmetric in V and W. And V dot V is always positive unless it is V is a zero vector when it is zero. V dot B is strictly positive. So these are all from the beginning of education, we know, mathematical education. Okay. So one calls two vectors orthogonal or perpendicular, preferring what word you prefer, if this dot product is 0. So I'll write like this or dot also. I'll mention which product I'm taking usually. Similarly, on Cn, you have another inner product. So here you have the bar here. Okay. So as you know, you would have seen enough lectures by now to know the importance of this inner product. So the only thing is, again, I point out that it is, although it is symmetric, it's sort of bar symmetric in W. That means you interchange W and B, it becomes bar of this. And if you do twice, it becomes the same. That means bar karne se, it will back to the normal. Okay, so VW is WV bar. And VV is real and strictly positive. Except, of course, for the zero vector. Okay, so far, since it is very elementary, I can go this fast and maybe even faster possibly. In what follows, so we'll just take either R or C, and this denotes a corresponding inner product I mentioned above. Usual canonical inner product we think of, the two cases. So what is an orthogonal basis of this n-dimensional vector space? You know that Vi and Vj are orthogonal, that is inner product is 0, and with itself, the inner product is 1. Okay, so this is both for F as R and C. The notion of orthogonal basis is there. Orthonormal if it is the unit. Okay. Orthogonal simply means this. They may not, Vi may not be 1. It is something non-zero, positive, Remember, even for complex inner product, Vi is real and it's positive. Okay. So in convention, write the vectors usually as columns, because when you write matrices, you always used to multiplying a matrix by a column on the right. This is a convention. You can do the whole theory the other way, but whatever we are used to, it's better to continue with this, because we have to stick to one convention. Okay, note that when you look at net product of VW, it is just the matrix V transpose W. V is a column vector, so V transpose is a row vector. So this is 1 cross n cross 1, so it is a scalar here. Similarly, V transpose W bar, summation Vi Wi bar. That's the inner product of V1 V2 Vn and W1 W2 Wn in Cn. Given this, what is the connection with the metric groups? An n cross n matrix is an orthogonal matrix if and only if this is the corresponding. So E1 E2 En is a canonical basis. GE1 GE2 is an orthonormal basis. Okay, so GEI GEJ is 0 for I not equal to G, and GEI equal to 1. Okay, this is one way of defining. Okay, so viewing that, an orthogonal matrix is nothing but an orthonormal basis. Think of it like that. Okay. Similarly for UN also, sorry. So I just wanted to say why it is like that. For UN also, the usual Cn inner product, it is like that, orthonormal with respect to that base. So just to quickly recall how, so look at VW and Fn and n cross n matrix, any n cross n matrix with entries in your field. Then, sorry, misprint here, GWs. That's one more reason I didn't upload the notes. I look at all the typos and then correct them in 5 minutes after the lecture and upload. GV transpose GW. So we just V transpose G transpose. So because this is an orthogonal matrix, if it is an orthogonal matrix, this is the same. And conversely, suppose this is equal to this. That would mean that this is equal to V transpose G transpose GW equal to V transpose W for all VW. Okay. From this, you want to say G transpose G must be the identity matrix. Okay, remember this is some n cross n matrix. This is 1 cross n, n cross n, n cross 1. So you want to say this is, so you have to apply it to various unit vectors A and EJ, and simply notice that AI transpose G transpose is nothing but equal to this. Simply means this is the ijth entry, as you know. In other words, this is the G transpose G is the identity matrix. So just to tell you that, okay, you don't have to think, you don't have to take it on faith or from memory or something. It's just completely trivial. Matrix is orthogonal if and only GE1, G2, GEN is orthonormal basis. Orthonormal basis. Remember, I'm not taking SON, I'm taking only ON. Still, it's an orthonormal basis. Okay, some remarks here. So just to say about general groups, see, since I don't want to discuss in detail about general fields and so on, but it's good to mention at this point a few things about orthogonal group. So first thing is, in Rn you can recover the inner product from the length simply by doing this, because you can divide by 2. You know all that, right? Usual. So this is if it's an inner product, then you can divide from the length, you can get the angle. Okay. So set of all linear transformations which preserves angles or lengths. Same thing you can say. Instead of saying preserving inner product, you can say what we saw was it is preserves inner product, but the same thing as preserving length, because you can get back this. Okay. So, so preserving lengths. So that is sometimes we say these are isometries. But anyway, we'll come to the isometries now soon. Just as linear change of variables. Okay, if you have x is in Rn, and px does not change the quadratic form. So what happens to the quadratic form? That means the set of values it takes. What is it meant by quadratic form? This is a quadratic form summation xi square, right? Because x is like that. When p is in On, we know that it is not changing this. Similarly, to take a more general quadratic form. So look at something like summation aij xi xj. So this means homogeneous polynomial some n variables, homogeneous of degree 2. The aij's are this. So those which leave this, any linear change of variable which when you make on these variables, if it remains the same value, that means q of px equal to q of x. Okay, suppose it's true. Such a matrix P obviously will satisfy this condition. Okay, because you can think of this condition is x transpose ax. This is nothing but x transpose ax. So q of px will mean instead of x, you'll take px. So it will be x transpose p transpose ap x. It should be x transpose ax. So all those matrices P for which q of px equal to q of x means all those matrices P for which this happens. So this defines a general sort of orthogonal group corresponding to a quadratic form Q or the corresponding matrix Aij. For example, you might, real numbers, you can take forms which are not positive definite, like in the inner product was positive definite. We would have taken some positive signs, some negative signs. Then the corresponding matrices which leave this form invariant, that is, which satisfy something of this kind, this will be called the group OR n minus R. R positive sign, n minus R negative signs. Again, convention, you can call it O n minus R if you like. Positive is not more special compared to negative. Okay, so anyway, quadratic forms over R are classified by these two numbers, n and R. For real numbers, these two numbers are enough to classify quadratic forms, whatever classification means. Classification really means the set of values they represent and so on. Okay, for general fields, the classification is much more complicated, and it uses something called the Witt invariant. Due to this, Ernst Witt was a great mathematician, and here's one of the things he is known for is proving that so-called cyclotomic polynomials are irreducible. This usual proof that we learn is due to him, beautiful proof. But anyway, he's done many things. His main contribution is the so-called Witt invariant. And again, to break the monotony, let me give a cartoon here. So here is our quadratic forms. So it says, I don't care either way about jokes. No offense meant, it was a harmless joke. So you are Witt invariant. So of course, here it is WIT. Somebody who doesn't understand jokes. Okay. Come to Hamilton's quaternions. So this is the usual. H is a set of Hamilton's real quaternions. Okay, people who study quaternions over different fields, and many more quaternions are there. But the first quaternions are the real quaternions. Consists of 4-dimensional real vector space on which we have a multiplication which is not commutative, and it forms what's called a skew field. So it's almost like a field. That means all the non-zero elements have multiplicative inverses. Only thing is things don't commute with each other, as you know. That's the word skew. So nowadays they also call it division algebra. So they have this, as you know, it's well known, they have this basis of this vector space with both basis of 4 elements. Let's say 1 ijk, and these symbols have this property ij is k, which is minus of ji, etc. So this defines a nice skew field. Okay, there is an addition, there is a multiplication. Since it's a vector space, of course, we have an addition and a scalar multiplication by r. Every element is of the form a plus bi plus cj plus dk, where a, b, c, d are real numbers. So this is the real quaternions. Now here is where the as soon as he discovered this, he embedded this in a stone which is still there. Here, as he walked by on the 16th of October 1843, Sir William Rowan Hamilton, in a flash of genius, discovered the, I can't read it here, yeah. So formula for quaternion multiplication. I square equal to j square equal to k square equal to ijk equal to minus 1. So this is well known. Just to say that here stone still exists. Okay, two quaternions can be multiplied by using the multiplication for ijk, because you are using distributivity and associativity, of course. Okay, so this to multiply by this, you just have to use what is I times j, etc. and gather them together. For example, when you multiply this by its sort of conjugate, instead of each of these, you change the sign, it becomes this. So very much it reminds you of complex conjugate. So there are a lot of similarities and a lot of things you can get out of it. There are also some little changes, some differences. So as I said, this is sort of generalization square of the absolute value of complex number. So suppose you define this kind of bar to be, don't change the sign of this constant term, but only this other quaternion term. So this part of this, the term which contains ijk is called pure quaternion. Okay, the pure quaternion term, you just change the sign. That's the bar. When you do that, what happens is you have this condition: multiply two quaternions and take the bar. Then it is product of the bars in the opposite direction. Okay. Of course, in our complex numbers, it is usual alpha bar, beta bar. There is no change. Here it is opposite direction. So it's an anti-homomorph. So because of that, you can say alpha alpha bar times beta beta bar. You can take this alpha beta times alpha beta bar. Because alpha beta bar is how much? Beta bar alpha bar. So alpha beta, beta bar alpha bar. Beta beta bar is a scalar. So you can just take it out. Scalar means a real number. You can take it out. That is why it is like this. So because of that, this number, alpha alpha bar, which you can call as the norm of alpha, is multiplicative. So this is precisely the statement that, okay, so if you want to view this, alpha alpha bar is this. A is summation ai square. Beta beta bar is summation bi square. So whatever alpha beta is, suppose alpha beta is this quaternion, then alpha beta times its bar is nothing but summation ci square. Fine. So you just have to calculate what is C0, C1, C2, C3. You can just gather together. It will be a complicated expression. It will be looking like this. C0 will be this. So now that tells you something, namely that sum of 4 squares times sum of 4 squares is sum of 4 squares. Now we can use it over various things. You can use it over integers. Sorry. So there is this famous Euler's identity, which tells you this square times sum of 4 squares and sum of 4 square is equal to sum of 4 square, where C0, C1, C2, C3 are magically like this. So there is no magic to it. Once you know quaternion multiplication, there is no magic to it. That completely reveals. So this is just giving that any two positive integers that are expressible as the sum of 4 squares, product is also expressible. Using that, one can show that every integer is expressible, every positive integer is expressible as sum of 4 squares. Okay, so this is what Euler wrote, and anyway. Okay, this is an anti-automorphism I mentioned here. So now, once something is homomorphism and anti-homomorphism, still one can do the following thing. This map satisfies multiplicative, right? Norm of alpha is multiplicative. That's what we saw just now. Also, bar is not a homomorphism, it's anti-homomorphism. Alpha times alpha bar becomes a homomorphism. That's what means that it's a satisfying this condition. So because of that, we can easily use things like, you can write the inverse in terms of this norm. This is a scalar here. Okay? This is now summation a square plus b square plus c square plus d square. Okay. Now look at this norm homomorphism and go back here. Norm is this homomorphism from your quaternions H to real numbers. So non-zero elements go to non-zero elements. And you can even look at the kernel of this homomorphism. That means what? Those of norm 1, quaternions of norm 1. What is that actually? A plus bi plus cj plus dk, a square plus b square plus c square plus d square. So essentially, as a 4-dimensional vector space, you're looking at unit vectors there. So it is nothing but S3. S3 is the, okay. S3 is x0 square plus x1 square plus x2 square plus x3 square equal to 1. So as what we are saying is kernel of this, which I denote like unit quaternions of unit norm, is nothing but unit sphere in 3 dimensions, of 3 dimensions. When I say in 3 dimensions, I should be careful. What I mean is of 3 dimensions. It is living inside 4 dimensions. Okay, this is again a little comment. Hendrik Lenstra is a top class mathematician still alive, and he makes very interesting comment during his lectures. One of them is this: suppose the Martians defined the complex numbers by adjoining a root of -1, they call J. And when the Earthians and Martians start talking, they have to translate I to be either J or minus J. So we take I to J because I think that's what the scientists will decide. It was later discovered that most Martians are left-handed, so the philosophers decided better to. So this is a higher order joke actually. So whether it's J or minus J is up to you, what choice you make. Just like saying, let I denote a square. So you're fixing. Let us now prove the following thing. So you know, remember the group SU2. SU2 is the group of 2 by 2 unitary matrices determinant 1. Okay. And you have unit quaternions. Remember, unit quaternions were identified with the unit 3 sphere. Now we also have the group SO3, 3 by 3 real matrices, transpose equal to inverse, determinant equal to 1. Okay, and S. So there is a homomorphism from here to here. This is quite important in physics also, whose kernel is plus minus identity. So this is the unit 3 sphere S3. This is also unit quaternions, and this is just a, so this is just a 3 sphere is a double cover of this. Think of it like that. So what we call a spin 3 or something is your 3 sphere. Okay. So remember, just to mention this, how this homomorphism comes along, any element of SU2 is going to look like this with the condition transpose equal to bar inverse and also determinant equal to 1. When you put these conditions, it has looked like this: A plus IB, A minus IB, C plus ID, minus C plus ID, and determinant equal to 1. Determinant is just this. So we know what to do naturally. You want to map this to a quaternion. So best way to do is map it to this quaternion: A plus BI plus CJ plus DK. This matrix is mapped to quaternion this thing. And you can easily check that matrix multiplication here leads to the quaternion multiplication here. So it's a homomorphism. This theta is a homomorph. Just sending it doesn't matter, but sending in such a way that multiplication here goes to multiplication here. Quaternion multiplication here. And okay. Image is contained in unit norm because determinant is 1 here. SU2 means. Okay, you can easily check that it is 1, 1. And it is also on to unit quaternions because you can just choose the corresponding matrix. So in other words, we can easily see that SU2 is a unit quaternions, isomorphic to unit quaternions. Now we want to know the second fact, which is that there is a homomorphism of SU2 to SO3. How do you get it? The natural way of viewing it is in terms of what is called a joint representation. That is, you look at matrix of SU2 and you look at a vector space on which these elements conjugate. So let me just come to that. Group of non-zero elements acts on the 3-dimensional real vector space generated by IJK. By conjugation, you see, elements of non-zero quaternions act on by conjugation of the 3-dimensional vector space of pure quaternions, IJK. So this is actually the Lie algebra actually. So we may think of this as acting on this space, and we have homomorphism. Okay, because we have this already the homomorphism. This gives an action on homomorphism to GLV. V is this vector space generated by 3 elements IJK. When you can explicitly evaluate it actually. How do you explicitly evaluate it? It's just conjugation, right? So when you look at conjugation of I and J and K, which is the basis of this vector space, by a quaternion Q, what does it look like? Oh, there is a misprint here. Q equal to theta G, equal to here, equal to. So let's say G corresponds to this quaternion, right? Theta G is this quaternion. So we have to calculate Qi, Q inverse, Qj, Q inverse, Qk, Q inverse, and then write the corresponding matrix. Turns out to be this complicated looking matrix. So if you want explicit homomorphism from SU2 to SO3, this is going to be that. We can check that by brute force calculation that this is a homomorphism, this is a matrix in SO3. That is, it's an orthogonal matrix and determinant is 1. So you can imagine how much calculation is necessary. But I want to say that conceptually, you can prove things without doing this calculation. Okay, so for example, the fact that it's orthogonal matrix is what? When matrix is the transpose is inverse. Now look at the transpose. The way the matrix looks like, transpose is inverse. When you have bar here, BCD will change to their negatives, and you see what happens here. Okay, so I just leave it to you to check this, and during tutorials we'll again check this in another way, conceptual way. The fact that this rho G is an element of SO3, determinant 1 matrix, and it is every determinant 1 matrix in SO3 is of the form rho G. So on 2 also. So there's an isomorphism, and the kernel is plus minus identity. And I say onto homomorphism is kernel plus minus identity. Kernel is plus minus identity is very easy to check because what are the things commute with I, J, and K, because you're looking at conjugation on I, J, K. You can just say any quaternion which commutes with all I, J, K has to be a scalar only. Then you'll, and once it is unique quaternion, the scalar with the unit quaternion must be plus minus 1. So as I said, final determinant assertion to show that determinant of rho G is always 1 is proved by direct but messy calculation. But I mean, this is the exercise, determinant 1. So, but then we can use topology, the fact that SU2 is nothing but a 3 sphere, and the fact that this map rho that we have written, rho of G is this, right? Okay, these are continuous functions. So image has to be in a connected set. One from a connected set, a continuous function you take, connected set. O3 is not a connected set. Okay, so the image contains some element of SO3, like the identity matrix, then it should be fully inside SO3. That's what a topology means, topological proof means. Okay, so let me go further. We can discuss this a little bit, the second star here during tutorials. Now this kind of topic I'm looking at, exponential matrix proofs. Okay, so I said matrix proofs for us is a subgroup of JLN F for some field F and for some N. Okay, so essentially we are looking at various such matrix groups, and you know why matrices are going to be useful. We don't have to be told, because even if we have an abstract group, if you put it as a matrix group, you can manipulate much more easily. That's why matrices are very useful. That's why so-called representations are useful. So incidentally, when I talk about something about representations of groups, it has already been talked about by Professor Manish Kumar, but there will be some intersection, and hopefully I'll say things which are different also. Anyway, first let's come to the exponential of a matrix. You know that exponential function is the most kind of important function in mathematics in some sense. Okay, even when common man asks you, what is the constant which is most amazing or something, most important concept, constant, people always say pi, of course. As a mathematician, you would say E. Okay. In fact, pi you can get from E. Okay, you know that. Anyway, so let's look at. So anyway, so exponential map on matrices yields a bridge from what so-called Lie algebras to Lie groups. So in the Lie theory, it's very important, even in differential geometry, the exponential map. So I'll say a few things. First thing is, we just concretely define exponential map on matrices. Sorry. Okay, we know that usual exponential series is this. So we want to define the same series for a matrix A. Of course, infinite series for a matrix, what does it mean, right? You can multiply matrices Okay, you can take n power of matrix and add them, but finitely many of them. So, of course, to say again, you have to know about infinite series. So, you have to give a notion of convergence. First thing is, we suppose we take in this series, infinite series.
क्लास में कोई नहीं खुला है आज.
Somebody is talking. You have a question? Okay. Munir Nabi, do you have a question? You're talking? Okay. So exponential series is an infinite series here. Now, you can imagine some situation where the series becomes a finite series. What's a natural thing like that? Suppose you have this or Z, you have some object like a matrix, for example. Matrix, some power onwards, it is 0. These are called nilpotent matrices. Right? So, first thing was nilpotent matrices, you can just define. Suppose x power r is 0. We have exponential is just a infinite. This finite series. Degree. So, this makes complete sense. For example, you look at such a matrix, you know that this is going to be nilpotent. Upper triangular matrix with zeros on the diagonal will be nilpotent. We can calculate its exponential and so on. Turns out that fourth power is 0. Incidentally, if you have 4 cross 4 matrix, which is nilpotent, some power, of course, is going to be 0. Which power is 0? Definitely fourth power is 0. For all you know, third power it could be 0. It all depends on the rank and so on. Anyway, so fourth power definitely must be 0. Why? Okay, anyway. So exponential series for this matrix reduces just to this. And notice one thing, that this matrix has ones on the diagonal. So it's an invertible matrix. Any matrix with ones on the diagonal and upper triangular is invertible. Mr. Munir Nabi, I think you have some questions. Will you go ahead, or you have some questions? Okay, so this determinant is 1 here. So let's now look at general matrix A. As I said, to define series of matrices, you need a notion of convergence. So what we do is, given n by n matrix, you can give any number of course, a finite dimensional vector space. N by n matrices form a finite dimensional vector space, dimension n square. So any two norms are equivalent, we know that. So you can give convenient norm we give. Let's say this norm, maximum mod Aij is a norm. So with this notion of norm, we'll check for convergence of series. So we can note that product of two matrices are norm bounded by this. By the way, the n is fixed number here. Okay, don't think that n is going to infinity. N is a fixed number, size of the matrix. So norm gives a notion of distance between matrices, and by this you can easily check this. Up till kth term you add, and then you find that for every k you have null this bound. You can easily check that by usual normal real numbers. Looking at real numbers. So because of that, you know that what is meant by a series. This is the limit of this finite series. So because of that, you have this converges, and that is what we call as e power a. You know that this series converges as k goes to infinity with the help of this norm, so that we call as e power a. So let's look at some properties of the exponential of matrices. Okay, maybe I should mute the person. I don't want to mute people, but okay, thank you. Sorry about that. So maybe at the end I'll ask who wants to unmute and ask questions. I'll do that. Right now, let me go ahead. Exponential of zero matrix is identity matrix. As you can see, because the series just has one term. Okay, so now look at PA, P inverse, such a matrix, an exponential of that, P will come out, as you can see. You can just see for finite series first, right? And then look at the limit. PAP inverse, exponential of that would look identity plus PAP inverse square by factorial 2, which would give PA square P inverse by factorial 2. So that means P can be taken on the left and P inverse on the right, and we have this A and A square by factorial 2, etc. That's why this is true, and you can take the limit. If B is upper triangular, E power B is also upper triangular, because what you're doing is taking powers and adding them. So zeros remain zeros below the diagonal. Diagonal entries, of course, are just the exponential of the diagonal entries. In particular, since every matrix, okay, now here are complex numbers. Every matrix, you know that you can choose a basis so that it looks like upper triangular. Okay, this is simple linear algebra. You know that every matrix is upper triangularizable over C, over any algebraically closed field, or any field where all the eigenvalues exist. Because you want upper triangularized means diagonal entries are going to be its eigenvalues. So eigenvalues better exist over that field. So over C, you can definitely do. So then, using this second property, it's clear that determinant of E power A, E power trace A. Think for a moment. Anyway, we can, again, I thought of discussing this during the tutorial. This is a very important property, very beautiful and important property. Exponential of A has determinant, which is exponential of trace. So let's look at special cases of matrices, like for example, skew symmetric matrices. We have seen that A transpose is minus A. That shows one thing is there. What about E power A into E power B? It's not E power A plus B, because unfortunately, because A and B may not commute. Okay, when you want to write as E power A and E power B as E power something, that is there is a okay. I don't want to get into that. In Lie groups, it is necessary to know these things. So then you'll have something called Campbell-Baker-Hausdorff formula. E power TA into E power TB. In terms of when T is small, you can say E power T times something is a power series in T. Then you can look at what is the first term or the second term. So its first term will be A plus B, but what there is an error also, because you're assuming AB is BA, then it's just that term. So AB minus BA will come as the first term, etc. So it's complicated. E to the power A and E to the power B is a complicated formula. On the other hand, A and B commute, there is no problem. E to the power A and E to the power B is E to the B into E to the power A. Okay. Each term of the series commutes with each term of the other series. So this is the situation with A trans skew symmetric matrices, for example. A transpose is minus A. In general, A and A transpose may not commute, you know that. Only normal matrices. So A transpose is minus A means they commute. A transpose and A commute. In particular, all leading diagonal entries are zero, of course, this skew symmetric condition. So particular trace is zero. So for a skew symmetric, okay, let's look at okay, I don't know. I took it, my student. Okay, let's see. We'll take this, some example here. Yeah, not this one, this one. P and C, then you can. Okay, so ignore that. The example that she has written is not. Addition formula E power A plus B holds when A B equal to B. I just mentioned it's very trivial. If X is skew symmetric, because X transpose commutes with X, it follows that X times X transpose E power X plus X transpose. And this is identity matrix. That means what? But what about E power X transpose? What is X transpose square and so on? It is X square transpose, etc. X transpose cubed. So that means E power X transpose is nothing but E power X transpose of that. So because of that, you get this condition. That means E power X is an orthogonal matrix. So for a skew symmetric matrix, exponential is an orthogonal matrix. And not only that, the determinant is 1. Because determinant of E power this thing is E power trace of X. And just now notice that skew symmetric matrix trace is 0. Orthogonal matrix of determinant. That's what I mentioned. So this is crucial. So sometimes we call, okay, not sometimes. So the set of skew symmetric matrices is called Lie algebra of this Lie group of special orthogonal matrices, or even of orthogonal matrices. So Lie algebra is some kind of linear approximation to the group. Okay, and it's a tangent space at the identity for this group when you think of them as manifolds. Anyway, so skew symmetric matrices form the Lie algebra of orthogonal matrices. So as I said, one views as exponential map from the skew symmetric matrices, Lie algebra of the Lie group gives a homeomorphism from a neighborhood of the zero. So this actually is a homeomorphism from neighborhood of zero to neighborhood of identity. Why is that actually? So this is quite important because just giving a map is not enough. So is it 1, 1, 1, 2, and so on? Of course, it's may not be good everywhere, but near zero and near identity, it's a good map. Inverse of the exponential map. That means you can define an exponential called logarithm of a matrix which is very close to the identity. Logarithm of a matrix close to identity can be defined. That's what we mean. So how is that? Let me just see. This is actually from a book. The logarithm of matrix will be defined only for matrices near the identity matrix. Let's see how. So we know that logarithm series is here, right? So you want to know, it makes sense. When X is very close to identity, as you can imagine. So you'll take the same kind of norm that we had, and you can bound the norm when is look at the matrix Y, which is X minus identity, which is very close to zero, right? That's what we're taking. So let's say is less than equal to epsilon here. So we can say any general power is this, and you can just see the convergence of this series using ratio test. So it means this converges. So we have this series. This is a well-defined good matrix. So when X is close enough to identity, we have log X defined. Any matrix defines also what's called a one parameter subgroup. One parameter subgroup simply means additive homomorphism. I mean, a homomorphism from the additive group of real numbers to the invertible matrices. Okay. For example, I can give you one example of additive homomorphism. In 2 by 2 matrices, look at 1T01 as T varies over real numbers. 1T01. So this as a group is isomorphic to the additive group of R. So it's a one parameter subgroup. So similarly, in general, any alpha like this homomorphism from additive group R to this, and which is also C infinity. So smooth homomorphism. So these are topologies, both are. So both, it's a smooth is the word for usually for C infinity maps, such that. So what we want to say that in the case of JLNR, how does any one parameter group look like? I'm saying it is simply exponential of TA for some matrix. Let's see why. It's quite easy to see. And then once you have that, then alpha dash 0, when you calculate this, is A. It means once you have this fact, alpha t is of the form e power TA can be regarded as a tangent vector at the identity matrix. Because alpha of 0 is identity matrix. A is a tangent vector at alpha 0 to JLNR. So, in other words, set of tangent vectors to JLNR at identity is nothing but set of all matrices A, MNR. That's what this will show. And correspondingly, instead of JLNR, we have some subgroup of JLNR. And look at again this. Look at the corresponding A's that form the tangent space at identity for that group, for that subgroup. This is solved. And that tangent space is usually called a Lie algebra because this vector space also has an additional structure of Lie bracket, okay, which is useful. Anyway, so let's just look at this simple fact now. Any one parameter group, any homomorphism which is smooth, looks like this for some matrix A, corresponds to some A. So this elementary, once again from that book, I'll show you this. So as I said, tangent space is identified as this vector space MNR. Because the set of all A's, which are, you know that tangent space is nothing but speeds of all such curves. Alpha dash 0, where alpha looking at this. Set of all alpha dash 0 is the tangent space. Okay, so suppose gamma is a one parameter subgroup. We want to say there is a matrix for which A, so for which gamma u looks like e power ua. So what we do is looking at log of gamma u. Then sigma is a curve with gamma u is e power sigma u. We just need to show that sigma u is a linear, it's a line through 0. That is the form u power a, u times a. Okay. And that is just simple calculation. Calculate sigma dash of u from here by first principles, and you just get using the fact that gamma is homomorphism means gamma u plus v is gamma u times gamma v, which are used here. And log of gamma u times gamma v is nothing but log of gamma u plus log of gamma v. So both of these we used. and then it immediately comes out with this. That means sigma dash u, sigma dash 0. This simply means sigma dash u is independent of u. So sigma is indeed a line through that. Showing that gamma u is this same thing as saying sigma u is u times a. Okay, saying this is same thing as log is nothing but u times a. That's what you've done. So we have tangent space identity. JLNR is your MNR. And correspondingly, for any subgroup of JLNR, tangent space identity will be all the A's which are arrays like this. One parameter subgroups to that subgroup. So exponential map gives a diffeomorphism from a neighborhood of the zero map matrix to a neighborhood of the identity matrix. In this manner, tangent spaces of all these subgroups, various subgroups, SLNR, ON, etc., can be identified. Okay, so that's the advantage of exponential map. For example, let's see what it looks like. So if you have subgroup H of JLNR, I just now mentioned that tangent space identities, all those matrices in MNR, so that this happens. Okay, because that one parameter subgroup. In fact, this happens for small n of t. For all small n of t, if it happens, that is a tangent space. Dimension of Lie algebra is the same as that of the group considered as a manifold, because it's a local homomorphism there, local diffeomorphism from the tangent space. So here is the vector space, namely the tangent space to the linear space. Its dimension is space of the dimension of your group here as a manifold. So you can actually calculate dimensions of all these group ON and all those things by using the tangent space. For example, dimension of SO2N, this, okay. Oh, there is a misprint here, 2n minus 1, okay. O2N, SP2N. Okay, so we'll discuss this dimensions in the tutorial. The dimensions can be calculated using the dimension of the corresponding tangent space. Okay, I also mentioned things like you want to know about dimension, you want to know about whether the set is connected or not. Okay, just we earlier mentioned JLNR is not connected, JLNC is connected. What about ON? ON is not connected again. Plus determinant +1 and determinant -1 are different connected components. Okay, SON is connected, SUN is connected. So in fact, when you have connected things, you can even often prove it using different identifications. For example, SON by SON -1 can identify topologically with the SN -1, the N -1 sphere. Okay, this is actually very easy to see, but let me just leave it for the moment. Similarly, this is also a sphere. This is also, so inductively we can prove connectedness of these groups, SON, SUN, SP2N, and all. Okay, I already SP2N, I should have said SPN. My notation was SPN. Okay, anyway, 2n by 2n matrices. So inductively you can show when G by H and H are connected, then G is connected. Like that you can do that. This is quotient space, by the way. This is not a group. This is not a normal subgroup. You think of SON-1 as sitting inside SON as n-1 cross n-1 block in the top, for example, top left, and you have 0, 0, 0, 0, 0, and last entry being 1. That is how this identification comes. Okay, each of the compact connected Lie groups also has this following property. Okay, I mentioned the word Lie group. I'm not defined Lie groups. You don't need to know what Lie groups is. The groups that we have mentioned now, SPN, SUN, SON, etc., they are all compact and the connected ones among them. So I said SON is connected. I didn't say ON is connected. ON is not connected. So the compact connected ones have this following beautiful property, which can be proved in generality by common method also, but we will sort of verify it case by case in these cases, because this property is very important. Namely, each of these groups has the following property. There is a subgroup which is called a torus. The word torus, of course, we know that usual two torus is S1 cross S1, circle cross circle. We have, this is some Rn torus, and Rn copies of S1. As a group, it is isomorphic to this group. So it's an abelian group, okay, isomorphic to S1 cross S1 cross. This is called a torus. So of course, this is compact, connected, okay, abelian group. So compact connected abelian groups, they are very nice because The exponential map actually gives an isomorphism from the whole Lie algebra to this. Anyway, so it's a homomorphism. Addition there becomes multiplication. So abelian group is a product of some number of copies of S1. That is called a torus. So each of them has the following property. There exists a torus subgroup. Not only that, the tori which are of maximal possible dimension. Okay, so you might have a S1 R copies of S1, and it is not contained in any other subgroup, which is then it's called a maximum, which is also torus. Then it's a maximal torus. It's one fact that the maximal tori all have the same dimension. Okay, same number of copies. Not only that, they are actually all conjugate inside your group G. You take one of them, any other subgroup isomorphic to maximal torus, a maximal torus would be just a conjugate of this. And not only that, the union of this conjugates of a particular maximal torus. Union of conjugates of a particular maximal torus is also union of all maximal tori, because everything is conjugate. Union of all maximal tori is your group G. So your group is built out of one maximal torus and its conjugates, if you like, or all maximal tori. So it's very useful in any compact connected groups or of this form. So as I said, although there is general proof, we can look at it for a case by case. So first thing is, this maximal torus, as I said, all have same dimension R. Okay, that R is called the rank of the group. For example, you'll find that rank of UN is n, because a maximal torus inside UN will be e power the diagonal matrices e power I theta 1, e power I theta 2, e power I theta n. Diagonal matrices like here, because special linear, special unitary, so one dimension will go off. One condition will come. Rank of SU1 is n minus 1, rank of SPN is n times this rank of. Dimension is this and rank is this. Okay. This is already recalled, but rank is this. Okay, so each of the connected compact groups, we have this property. G is a union of its maximal tori, I mentioned just now. All maximal tori are conjugate, and their union is the whole group. So let's see how to do that. Maybe okay, let's do one or two facts we can do, and maybe some others we can do during tutorial. See, tori, what property they have? Torus is nothing but S1 plus S1 plus S1 as a group. Now you know that in a circle we have irrational angles. Circle is the e power I theta. Irrational angles. Look at a cyclic group, then it will be an irrational angle. That cyclic group is going to be dense. So same fact can be proved not for a single S1, but copies of S1. So any torus is monogenic. Monogenic simply means have a cyclic dense subgroup. So there is a single element properly chosen so that the cyclic group generated is dense over S1 cross S1 cross. So they have this very beautiful property they are called monogenic. Not cyclic, but cyclic group is dense. It can't be cyclic because this is uncountable, this is countable. Anyway, so these are monogenic. So to say that two maximal tori are conjugate, what you have to do? You have to say that take two maximal tori. Take one, any element here which is a generator in this sense. That is cyclic group generator. There is cyclic group generated is dense in that torus. Take such an element Y. You want to say Y is in the other torus. Y is in a conjugate of the other torus. Okay. And that is how it is proved. So what happens is, if you have proved this already, suppose you have proved that for any maximal torus, G is the union of this. Then any element is of course in some conjugate of your T. So take any other maximal torus, take its generator, some generator, that's in one of these, you are done, because cyclic group is contained in that. So this is closed, that means closure is also contained in that. That means one maximal torus is contained in a conjugate of this maximal torus. So it will be equal. Because conjugate of a maximal torus is also maximal torus. It cannot contain another maximal torus properly. So this is all. Once we have this property, that for a particular maximal torus T, G is the union of conjugates of that maximal torus, we also have that all maximal tori are conjugate. Okay, this is so the first fact implies the second means. First fact is this fact, G being union. Second fact is union of its maximal toric. Or rather, any two maximal tori are conjugate. You can think of that as a second fact. So this is, we need to prove this. Okay. So so you have to produce a maximal torus, show that G is union of conjugates of maximal torus. Remember these things. So these are all should strike you that, in a finite group situation, we have a group and a proper subgroup. Group can never be a union of conjugates of this proper subgroup. These are infinite group. That's why it's possible. So, for example, first fact that this is in the case of UN. Suppose you want to prove this. So, what is the maximal torus here? The diagonal matrices in UN. So, they're of unit. They're all of mod equal to 1. So, this is a copy of S1 cross S1 cross 1 n copies, right? That is your torus, maximal torus T. To show that UN is conjugates of this means what? Any unitary matrix can be conjugated to a diagonal matrix. And what is that fact? That is nothing more, nothing less than saying that each G admits an orthonormal basis of eigenvectors. Because you take a new basis, that means you are conjugating. Okay, having a diagonal matrix simply means they are all the vectors E1, E2, En, the canonical basis vectors are eigenvectors. That's what diagonal matrix means. To say that it can be conjugated into means you take a new basis. So means you can have a basis of eigenvectors. Now, how do you prove that? You can just prove by induction. You know that everything has an eigenvector. Take an orthogonal complement of that one-dimensional space and go, etc. So I will check it for SON, for example, because the diagonal torus here is much easier here. For SON, it's what does the maximal torus look like? Okay, so moment's thought will tell you, but we'll discuss it in tutorials, that maximal torus for SON is going to look like blocks like this. Cos theta 1, sin theta 1, minus sin. Cos theta, sin theta, minus sin theta, cos theta. 2 cross 2 blocks like that. Because you see, we want real group, right? It's a real group of real matrices. These are all complex. Really, cos theta, sin theta, minus sin theta, cos theta rotation matrix. Its eigenvalues are e power I theta and e power minus I theta. Anyway, so we'll check this fact for, as I said, we check this case by case. For UN, it is just this fact that any unitary matrix admits an orthonormal basis of eigenvectors, which is proved by induction. For S1, we'll check. Okay. Similarly, it can be checked for SPM. Somebody is okay. So groups UN are simply okay. So in the notion of topology, they are simply connected groups. Okay. So they don't have any covering spaces. I don't say much more about it, except that to mention the fact that SON is not simply connected. It is a very interesting double cover. There is a group called spin. There is a homomorphism of spin and SON, which is onto and kernel is plus minus identity. It's called spin group. But to define the spin group, see, SON is a matrix group contained in SGLN. But to define spin group, it's not so easy. So you have to. So you might even ask, is every group linear? Can you just put inside SGLN? Because there are many groups that are not linear for many trivial reasons. We will go into it during the last lecture also. But just to mention right away, suppose you look at a group like SL2R, 2 by 2 real matrices determinant 1. This is of course a linear group. This is already given as matrix group. But when you view topologically, it is not simply connected because SL2R is homomorphic to SO2 cross R, like that. R2, sorry, SO2 cross R2, 3 dimensions. So R2 doesn't matter. So SO2 matters. SO2 is S1, which has infinite universal cover. R covers S1. So SL2R has universal cover, which is infinite. That means there is a big group from which from that group to SL2R, you have homomorphism, which is onto, and kernel is actually like Z, because fundamental group of S1 is circle, so Z. So it's an infinite cover of SL2R called SL2R tilde. That universal cover cannot have any faithful linear faithful homomorphism to 1-1 homomorphism to JLN for me. Okay, once something has a 1-1 homomorphism and you have some finite cover of it, you can always put by induced representation something you can do. But infinite cover, it's not possible, may not be possible. So SL2 or universal cover is not a linear group, meaning it cannot be put in one way into a JLN. Just mention. In a case, SO1 case, spin groups are there naturally defined through what is called Clifford algebras, which we don't go into. It's very interesting theory. Just this case. So here is a person who is selling the computer and says this computer is really exponentially fast. So it's really exponentially fast means then I have to log out instead of just logging out. Take one more log. Okay. So I sort of there is some time, but I'll sort of finish here. So we haven't talked about Jordan matrices. Maybe during tutorial we'll have something to say about Jordan canonical form, because you see exponential map, what properties it has. For example, which matrix is not an exponential? Which matrices are exponentials? This is important. We know something about local behavior and all that. Okay. So, for example, as you know, over complex numbers, every matrix can be put in Jordan canonical form. So you have this Jordan block. Jordan block, is it an exponential of something? But this cartoon I liked a lot because you see, people who have seen Michael Jordan. This is Michael Jordan, the basketball person. So this is Jordan block. He's blocking on. Okay, so I think I will stop here. So I mentioned some of these cartoons are made by Vidur many years back, 11 years. Those pictures I kept. Thank you. Okay, so I'll stop sharing here. What I'll do is I'll look at the typos, correct them, and send and share this file. Actually, upload this file and the tutorial in the next 5 minutes after we are through. But if you have questions, do ask. If it is long enough, then I'll say we'll discuss during tutorials, or it might be in the tutorial question. Otherwise, I'll myself anyway. So I hope people can come forward when I mention a question to say something. So anybody has any questions? We have actually 7 minutes, but feel free to. So should I unmute? That's what somebody